these are predictions of inflation. The universe must be uniform, homogeneous, and flat. Flat means parallel lines do not intersect. And it was confirmed by observational data. Okay? The universe produces these perturbations, and they have just right spectrum, which was found also experimentally. So there are several different predictions of inflationary theory which were confirmed. So now this is just, well, make a moment of relaxation, because the most complicated part is still to go. So now is, well, now let us summarize where we are at the moment. So here is how we look at the universe. This is here, we're sitting on the Earth, and we look at the sky, and we see galaxies and we stars, and we're just observing it, and far away from us, a Big Bang. But we are observers sitting here. We are not traveling very far. So when we are looking at the universe, we use our observation like a time machine. Because when we are looking at our sun, we see the sun as it was several minutes ago. When we are looking at distant stars, we see the stars many hundred years ago. When we look at galaxies, we see the galaxies as they were shining several billion years ago. And then we look further, and we see this primordial fire created during the Big Bang. This is what these people photographed, this satellite experiment. They photographed the sky. They see these tiny inhomogeneities of temperature there. This is the maximum which we can do, or so we thought. And this is the beginning of everything, the Big Bang. Now, the new story is that what inflation tells you, that this is how it looks. There is something beyond this crystal sphere. There is something beyond this wall of fire. Because when the universe was first born, it was inflating. There was no fire yet. Fire emerged after this process of oscillation of the scalar field, creation of particles, reheating of the universe. But during stage of inflation, the universe was expanding from this size to that size with zero temperature yet. So on large scale, very, very far away from us, there is still space filled with a scalar field which is not yet oscillating, which is slowly going down, and the universe is exponentially expanding there. And if we look even further, we will find the parts of the universe where fluctuations are so large that they reproduce new parts of the universe ever and ever again. Now, when we go back, so what happened? Previously, we were like wolves. We were surrounded by fire. And you know, at least so fairy tales tell us, that wolves do not want to go through the fire. They somehow have this instinct. They do not jump over the fire. So we were like wolves separated from inflation by this fire. We thought that everything is this part. And now we know better. Now we know that, well, at least we believe that we know better. Now we know that infinite universe is beyond what the satellites show us. They show us that just a tiny, tiny, very big, but tiny, tiny part of the whole multiverse. Now, here is something else. When these quantum fluctuations, when they are very large, now, first of all, we already right now established that these quantum fluctuations existed, that they were stretched, and that this was experimentally verified. So now, when we said that these quantum fluctuations existed, in the places where they are large, they can modify, well, scalar fields which exist in the universe. Like, for example, in this model, this is a model which was considered by many people like a popular theory of unification of different forces long time ago. Never mind all of these symbols. It is not important. What is important that the scalar field may be here or here or here. If it is here, then there is no difference between quarks and electrons. There is no difference between strong and electromagnetic interactions. We cannot live in this part of the universe. If we are sitting in this place, then there's totally different story, totally different laws of elementary particle physics. If we are here, then this is the universe of our type. So what happens? During inflation, quantum fluctuations bring you from one place to another, and then when inflation is over, you fall down either to this minimum and live here, or to this minimum, and then we cannot live there. Somebody else may be able to live there, but we cannot. So the universe, even if it starts with a red universe, because of the quantum fluctuations and inflation, it becomes multicolored. And this is just the final image of a set of other computer simulations which we were running some time ago. So this is a red part of the universe. This is a blue part of the universe. This is the boundary between the red and blue. There is a high wall on the boundary. So if you are in the red minimum, the distance from here to the wall is exponentially large. You will travel, this is like 10 to the degree, this number, okay? You will travel long and long and long time, and then you will come to the boundary. But instead of the custom officer, you will see the wall. It's very difficult to penetrate the wall. But if you're young and stupid and have lots of energy, you penetrate the wall, you find yourself in the blue universe, and you die. Because in this blue universe, laws of elementary particle physics are different. Your electrons do not live there. Your protons do not live there. You do not live there. So, yes, we cannot go there and test, but that's how the universe looks like. And in some parts of the universe, laws of physics are not fixed yet. They're jumping all the time and inflating all of the time. So these high peaks, they correspond different small big bangs, which are happening all the time right now. Now, this theory was popular among some cosmologists. So we studied it with Juan Garcia Bellido somewhere in the beginning of 90s. And it was a good theory for our purposes. But not many people wanted to go this way because it's kind of too much. I remember when I was in Lebedev Physical Institute, and they wanted to promote me to the second range position, and they asked me, so what do I do now? And I told them, oh yeah, I study the theory such that, well, the particle coupling constants and the masses of electrons are different in different parts of the universe. And they looked at me like that and say, yeah. But then they promoted me anyway. So what we learned during the last 10 years, that the string theory, which is the most popular, or at least it was, or well, many people consider the best candidate for the theory of everything. We do not really know, but that certainly right now is the best that we have. Does not necessarily mean that it's true, but it's the best, so we try to find out what the consequences of this theory is. And until approximately 2003, we did not know what are consequences, because in all of these versions of the theory, our universe fundamentally was supposed to be 10-dimensional. We know that our space is 3-dimensional, and there is one time. So it's 3 plus 1 makes 4, not 10. So the string theorist will tell you, but other 6 dimensions are tiny. That's why you do not feel them. You cannot move there because the dimension is very, very small. And then we would ask, but can you explain us how they got tiny? And the answer was, well, we do not quite know, but we will probably explain it to you next year. And then continue and continue. And then people got nervous. And then eventually, in 2003, a group of 4 different people at Stanford, I was a cosmology consultant there, but there were, well, the names are Kachru, then Kalash, she is my wife, and she is just arriving as we speak in Madrid right now. And then me, like a cosmology consultant on the group, and there are some other professor from India, Trivedi. We found a way how to keep these 6 dimensions small. But once we found the way, other people estimated how many ways you can do it. See, these 6 dimensions, you probably can do it this way and that way. Okay, so this is the picture which illustrates the complexity of it. When you have 6-dimensional space, there are many possible topologies of this space and many different ways to organize it. And when people estimated how many is many, they come with this number. Okay, so it's a little bit less than the number which I've shown you already, but it's a huge number. And for each of this number, you have different laws of physics, low energy physics. In one of these, you have electrons, in another, you don't have electrons. In one of them, you have energy of empty space, this high, another this high. It's like having a bookshelf with this number of shelves. You have this many possibilities to have vacuum energy. Now, these people who are showing us that now this vacuum energy is not zero. They produced the number, they measured this energy of a vacuum, and it came extremely small. In all our normal numbers, if you express it in units, which are the units with which we are working, it is something like 10 to the degree minus 120. That's totally almost nothing. How they managed to measure it, just enormous ingenuity of our experimental colleagues. I'm really starting to, how to say, admire them because they're so good in what they're doing. Now, so they found this tiny thing, but why it is so tiny? And now we know the answer. Actually, in some parts of the universe, it's huge, but we cannot live there because these parts of the universe expand so fast, then they tear apart the galaxies, they tear apart human beings. We cannot live there because of the rapid expansion of the universe. In some parts, this energy of empty space is negative, and these parts collapse so fast that you cannot have any time to ask a question. And as a result, we live in the place where we can live. And this is anthropic principle again, but now this anthropic principle makes sense, because previously, either you are thinking about God creating one universe after another until final success. And you may think, well, how is that the God will take such a special attention to a special type of monkey? Okay, so it is kind of strange. But now what we do, we know that the universe does it itself. So if you start with tiny universe, then the universe takes care of it. And then it produces itself in all of its possible versions. So this is a picture which I used in the 90s to illustrate the idea of the inflationary universe. You start with a tiny part of the space, and then it becomes exponentially large. And we can explain why it is uniform here, because you stretch all inhomogeneities. You stretch them away. You live in this expanded universe so large that you just like, well, okay, so this is something which inflation did. Now, these are quantum fluctuations which produce new and new parts of the universe. These parts of the universe produce other parts of the universe, and they all have different colors, because you can jump from one vacuum to another, from one ground state to another. This idea, I expressed it in '86, which was 25 years ago. In the paper written in the journal Physics Letters, I have written that some people who study string theory, they are worried that they have so many different compactifications of string theory. And then I said, But what happens there should be considered not as a defect of the theory, but as its advantage, because it allows us to explain why we live in the universe which we live right now. I've written 86, but nobody cared about this at that time. It was too early. People at that time at the conferences, they never used anthropic principle. They said, we never use a word in our work. A word, you know Harry Potter? Okay, so how was this? No, you never call the name of this evil person. No, you never call the name. So you never use a word in the sensible paper on anthropic principle. We started doing it like that many years ago. And again, together with Juan Garcia Bellido, we have written papers published in respectable journals where the first part of the paper were hardcore calculations. And in the end, we would say something. And by the way, if you buy the first part of the story, this one comes free. But nobody wanted to buy this free stuff. They thought that free stuff, probably there is a cheating in advertisement. Now that string theorists, they need it. They didn't want it, but that's what they need to make the theory consistent. So this is what Alan Guth, actually the first author of inflationary theory, he said, that our universe is a free lunch. Because you take, in his time, he thought that you need about like maybe 50 kilograms of matter to create the whole world. And then in the scenario which I suggested, you can do it much easier. Less than milligram of matter is enough to produce not one world, but infinity of worlds. And that's what I said like in '83, and again, nobody cared at that time. I said that this is like a free lunch, and it's actually eternal feast where everything is served. And I can confirm it that indeed in the hotel where this foundation have put me, in the beginning when I go there, I have an experimental proof of the multiverse here, just looking at the choice of the dishes. You need to be a guest of this foundation, I guess. Okay, so one sad story about this, that all these vacuum states, all these 10 to the 500 different states, according to string theory, they're all unstable, and they're all going to collapse. So this is a sad prediction for us. If we believe the theory, our part of the universe is going to collapse. How long it typically takes for the universe to collapse? 10 to the degree, and then you write your number. Okay, so usually it's a lot. So we have many other problems which can kill us before. We can solve some problems in Europe, we can solve some problems in the United States, whatever. So we have many more urgent problems to solve. But because of inflation, eternal inflation, the universe as a whole, this growing tree of the universes, it is eternal. So it's always going to reproduce different parts. So if we cannot live there, and maybe our children cannot live there, somebody else's children in far different, distant part of the universe are going to populate the universe. And now the final question. With all of this flashy story, cannot be tested? I already gave you part of the answer in the beginning, but then so the question is, can we test it? The theory provides, so far, the only explanation as we know of the smallness of vacuum energy. People were trying to find the solution of this problem for about 30 years, even before the measurement. They were trying to explain why vacuum energy is very, very small. So now we know the solution, and this solution requires existence of multiverse. You think about something simpler, mass of the electron. If mass of the electron were 2 times larger or 2 times smaller, life, as we know it, would be impossible. If the mass of the proton and mass of the neutron, the difference between them, would be just 1% larger or smaller than it is right now, say proton would become slightly heavier than neutron, life as we know it would be impossible. So it is really nice to believe into anthropic principle. But we cannot make any sense out of it if we do not have choice of the universe where neutron is larger than proton and the universe where proton is heavier than neutron. Now we have lots of choices. Therefore, I consider it as experimental proof of, at least this is the best explanation of many experimental theories.